This clicker question up, so please let us know what you think. All right, so again, we're just getting started here. If you could let us know what you think, give us your opinion here. I'll let this be open for just a little bit longer. So we got the, again, question about the quiz up here. So if you want to let us know what you think, please do it now. We'll shut it off here in a little bit. Just good to get everyone's opinion about this stuff. Okay, so let's go ahead and call time on that. And so again, like I was saying, I sort of like it. This is sort of the sort of distribution that sort of gives us. Usually, like again, I think there's a pretty good correlation between how you guys felt about it and how it ends up being, and so it's more like this sort of distribution here. And so it seems like there's still some more. I thought it was hard than sort of what they expected. So again, we're going to try to hustle and get everything back to you on Tuesday. And so we'll let you know more about everything then. Any comments about that? Yeah. What's that? So so I ask this after every test or quiz I give, right? And this is sort of the distribution that, when I get that, then the test is usually right around the average of like a C, and so it's a pretty solid test that I'm sort of happy with, right? At least, typically. I mean, again, I haven't, done this in the U.S. in a while, so maybe this is what Canadians think. I don't know. But yeah, so it's, like I said, it seemed like we had a little bit more over here than here. So we're grading it right now. It definitely, I looked over, it definitely looked better than the first one. So we'll see how it goes. Any other comments? And then just again, like I said, I do think Gauss's law is really tough. So I think as we sort of move on, it'll be a while till we get to something that's quite that tough. So that'll help too, I think. So we're going to move on and talk about electric circuits. So we had, just started talking about capacitance, and we're going to move on now to electric circuits more in general. And so the first couple of things, just some definitions. So I say this in the video, but a long time ago, people didn't really know how circuits work. So basically, people were able to do things with circuits before they really knew what was happening. And so they came up with this term called electromotive force, and it's just, it's the same thing as your voltage for your battery. And so sometimes the book will use a little script E, okay, for the voltage. And so it's just something I like to talk about. It's just basically the maximum potential difference of a battery or power source. And so it's, for our purposes, it'll be the same thing as the voltage of the battery. We'll deal almost exclusively with perfect real-life batteries. Here's the symbol for a battery on our circuit. So we sort of talked about the symbol for capacitors last time. A battery looks like this. There's a big end and a long end and a short end. And so it's generally known that this is the positive side and that's the negative sign. So that's the symbol for what we call this EMF or the battery. And so again, sometimes the book will call this your EMF or your voltage source, but it's all just kind of the same thing as far as we're concerned right now. So are EMF, voltage, and electric potential the same thing? Yes. And so that's just kind of confusing. Voltage and electric potential are the same thing. This is the sort of correct term. This is the units, and so it's just faster to say voltage, and then EMF is this historical thing that applies more to circuits. But really, for our purposes, there is no difference. A battery will be a potential difference, and we'll usually refer to it as having a voltage. Like my favorite is the car battery of 12 volts when I do examples. Can a capacitor be regarded as a battery? So that's a good question. So like last time we talked about how you can use a capacitor as a source to power something, right? But a battery, as defined, as we'll see in a few slides, is something that has a way to replenish itself. The capacitor, when it discharges, it'll end up being empty unless you charge it up again. So there's a difference there. So a battery and a capacitor have some similarities, but they're not the same thing. So electrical current is what we're going to talk about. We sort of described this last time and when we talked about how the capacitor charged up. So when we connect the two terminals of a battery or EMF in a circuit, okay, so some sort of what we call a continuous conducting path, charge will move throughout the circuit. And I just wanted to show you this here. Sometimes the book will throw this on you here. This is, how like if you have a flashlight and there's like two batteries in it, the symbol for that would just be sort of two batteries right next to each other. So sometimes they'll sort of throw two batteries in there, but it sort of works the same way, right? It's just like sort of doubling the potential difference as opposed to just having one or something like that. But if you connect a piece of metal, a conductor, to the two ends of a battery, charge will flow. And since there is a potential difference, what happens is the electrons on this side will start moving to go over to the positive side. All right? And this is going to be, a point of confusion. So basically, Ben Franklin, a long time ago, named the charges, and he didn't know anything about what was going on. And so he just, there was an experiment he did where there was two kinds of charges. He said, let's call this one the positive and this one the negative. If you could go back, it would be probably better to call the electrons positive, because it's going to lead to some confusions. But we'll sort of talk about that. But, so we'll sort of, for now, we'll sort of talk about what the electrons are doing, because they're the ones that are free to move in these conductors. And so electrons will start sort of moving, and that's what we call electrical current, this movement of the electrons through here. And so you can think about it as the battery pushing the electrons, and the electrons will flow in the direction of the positive terminal. So basically, if this is like a 12-volt battery, the electrons are at 0 volts, which means there will be an electric field set up that will want to push them to get to that 12 volts. Electrons want to get to a higher potential. They want to move up that mountaintop. How do you measure the electric potential difference and what causes this? So you measure it with a voltmeter, and literally what you do with a voltmeter is you put it on 2 different ends, and the voltmeter has a resistance, and it measures the current going through it, and then uses Ohm's law to calculate the potential difference, which we'll talk about in a little bit. And what is it really? So this is a battery here. So a battery is a charge, some sort of a separation of charge. So it's a system that maintains a potential difference of electrons on one side and bare nuclei on the other side. And the electrons, want to leave and go to the positive side. That's sort of how the battery works. And so we basically use that electrical current to do different things. All right, and so we had this question, when electrons leave the battery, how is it when they reach the positive side, that side of the battery doesn't become neutral? All right, and that's the difference between a capacitor and a battery. A battery has some mechanism. Okay, for most batteries, it's a chemical mechanism, but you can just think about it as like a little conveyor belt, all right, that moves the electrons back to that side. So sort of as an electron comes into here, it goes on the conveyor belt, and this conveyor belt keeps the charge separated such that it keeps that voltage difference. That's what a battery does. And again, that's usually a chemical process, but we're not going to talk too much about the innards of it, but you can just imagine it being like a little conveyor belt. Okay, so that's why the battery, and eventually the battery will, this mechanism will get weaker and weaker, and then the battery won't be able to do this anymore. So it does eventually die out, but we won't really talk about that, so we'll assume that most of our batteries are nice, sort of perfect batteries, but that's in reality how they would work. So just a little definition. The flow of these electrons is called the electric current, and the units is the ampere, and it's coulombs per second. All right, so if you imagine if there's like a big wire here in a circuit, and I just sat here and I sort of counted the number of electrons that come through per second, all right, and then I took the charge of an electron and divided by second, that would be the current. So it's how many, how much charge sort of passes by some point per second. And so delta Q over delta T, and of course, we'll have this be a derivative sometimes as well. All right, and so just a couple things to talk about, because we want to be able to understand this stuff conceptually as well as we can. So the drift speed. So if you read the book or watched the video last night, okay, the drift speed of electrons, so sort of how fast they're actually moving through here, is really slow. Okay, so we could ask this question, all right, like if I turn on a light at home, the light turns on almost instantaneously. Well, if the drift speed of the electrons is really slow, can anyone tell me why does the light turn on right away? Anybody? Yeah. Exactly. So what he said is there's electrons all the way throughout this wire. So basically, when I connect this circuit, electrons start moving over here, and they're moving pretty slow, but they move the next electron and the next one, and basically there's electrons sort of sitting here, and when these ones will move through the light bulb, okay? And they'll move through the light bulb and make it light up. And so the actual time it takes for that sort of motion to be noticed by all the electrons is pretty fast. It's roughly close to the speed of light. So even though the electrons themselves are moving very slowly, all right, this thing actually moves sort of right away. So that's exactly right. So let's move in then to our question from last night. So here's our light bulb. So when a light bulb is emitting light in a circuit as below, the number of electrons entering the light bulb is what compared to the number of electrons exiting the light bulb? Okay, so I think that's about everybody, and it looks like we're doing pretty good, so I'm going to go ahead and call time. If you haven't answered, please answer now. And so here's what we get for our results. Anybody want to tell us what they were thinking on that one? Anybody feel, yeah. Yep. So it's you can't, for us in this class, charge is conserved, so you can't lose charge. That's one thing. Anybody else have another way they thought about it? And there's lots of ways they kind of think about this. Yeah, up in the middle there. Yeah, so there's a rule that we'll learn as we go through, Kirchhoff's rule, that says that basically the charge coming in has to be the charge coming out. So let's look at some of the answers from last night. So I agree with the majority, B. And so here's some correct answers. So light bulbs do not take electrons to give off light. Rather, they utilize the energy of the electrons to give off the light, but not the electrons themselves. So since light bulb does not take electrons, number has to be the same. Another way to say that, I think, like the person over there, charge is conserved just like energy, meaning that the same amount they're going in has to go out. And so the incorrect answers were sort of along these lines. The law of conservation of current says that current going in has to be equal to the current going out. So here's somebody who sort of started off really perfect, and then they said, well, the charge has to go somewhere. That being said, some current will flow into the bulb and be lost as photons or heat. So less electrons would leave through the wire than would enter through it. And so you're not using the electrons to light up that light bulb. Okay, what you're using is the energy of the electrons. So as the electrons go through the light bulb, okay, they're going to rub against it. There'll be friction there. And if you set it up like in a light bulb, that's enough friction to actually light up the light bulb. When you do experiments like this in class, or in lab class, you know, if you're using a resistor, oftentimes if you touch the resistor, it actually gets hot. Okay, and so you're taking the energy of the electrons, not the electrons themselves. But we did pretty great on that one. Any questions? Okay. And so here's my model of sort of how conductors work. Okay, resistors or light bulbs or anything that we're going to be using the next couple of lectures works like this. And so this is Plinko. This is a game from The Price is Right. And so you can think of a resistor as being a combination of little sticks, okay? And these little sticks are like the atoms in there, okay? And so these are the electrons trying to move through these atoms, and the atoms get in their way, but the electrons have this general trend to sort of fall down. And so this thing is, you know, standing upright, and so as you drop electrons, they sort of bounce through here. And you can kind of imagine that how inclined this thing was kind of gives you a sense of you know, how much those electrons want to get down. And so I was really happy there was some game show a few years ago that really kind of shows this. And so let's watch an example here of this stuff in action.
Now, it is my pleasure to hopefully reward you with a lot of money. Let's drop them.
So they're doing this game show where they're dropping these balls through here, and it's kind of like how charges flow, right? Whoa. Look how excited she is about physics, huh? All right, and so this is sort of the picture that we use for a resistor. Sort of works like this here. And so this picture can be useful, I think, in a lot of different cases. And so here is the more, yeah, no, that's really fun video. But that picture, this is sort of the more formalized definition of it. So a resistor has a couple different things that the resistance depends on. And so here's the equation here. And so here's a picture of just a resistor. And a resistor could be just any piece of metal. You know, a resistor and a conductor are the same thing. Okay, we just call it different things in sort of the application of a circuit. But traveling through a conductor, electrons bump into things. These things are the nuclei of the atoms, and that slows them down. And so basically the three things that affect the resistance of something is this thing rho, which is the resistivity, which basically tells you something about the material, sort of how dense those bumps are in that sort of Plinko board. The length is L, so sort of how long it has to go through to get through it. And then A is the cross-sectional area. And so here's how we define the resistance. So rho tells you basically how difficult it is to get through the material. The longer it is, the bigger the resistance, okay? You got to get through more stuff. So the longer it is, the bigger the resistance. And then the cross-sectional area is actually, the bigger that is, the less the resistance is, because in a sense what's happening is it gives you more paths. In that movie with the lady, they could drop multiple balls through there because there was sort of a larger surface area there, and so you can kind of get more electrons going through. So let's see. So you mentioned that the wire was a conductor. Later you mentioned that a wire is a resistor. So again, conductor and resistor for right now are the same thing. It's just that we call it a different thing in relationship to circuits. It's something that, here it's something that's resisting the current, but it's going to be a conductor. And how does the material affect conductivity of surface area and conductor length determine resistance? And so it's that value P, or the rho. The rho is where that comes in. So different kinds of material have different kinds of resistivities. And again, that's just sort of telling you how much stuff is in there, how many of those little sticks are there to sort of stop the flow of your electrons flowing down. And so you can think about it, if I sort of put two of these Plinko boards together, okay, it's more resistance. It takes longer for these guys to get through. And by the same token, if I put two of them side by side, I'm giving more paths, so more electrons can pass by per second, okay? And so that's sort of the Plinko analogy to this equation we have here. And so let's look at this next one, which again we did last night. I think we did pretty good, so let's see what we think. So we have a skinny wire and a thick wire. It's made from the same material. Which case will have the largest current? What do you think? Okay, I think that looks like everybody again. So let's go ahead and call time here. I'll give me just a few more seconds till 1 minute. Make sure we get everybody. And again, I agree with the majority. And so this one here, you can think just basically the stuff we were talking about. Okay, so I know that the resistance equals this rho times L over A. So basically this question is, which one of these two cases has a bigger resistance? So they have the same material, so the rho is the same. They're the same length. Okay, if you look at the circuits, they're the same, two equal rectangles. And so the question is the area. And so the thick wire has a bigger cross-sectional area, which means more electrons can go through. And in the equation, it's on the bottom of the equation. And so the case with the bigger area is going to have the smaller resistance. And since the batteries are the same, all right, the one with the smaller resistance will have more current. And so it should be that the thick wire will have the more current. So questions on this, anybody? Okay. So just some, so this is your guys' comments. So the correct answer, current is the amount of electrons flowing through, bigger pipe, more current. I thought that was a great way to put it. In real life, wires have resistance too. The larger the cross-sectional area, the lower the resistance. So that was another great way to put it. and then some incorrect. The current should depend on the battery and not the type of wire, and since the batteries are identical. And so we're going to find that, as we go through with circuits, we care about the battery, but we're also going to care about the wires and the resistors. That's going to be really important to this. The thicker wire will have a greater resistance, and since the battery has the same voltage, okay, so again, the thicker wire means you have more paths to go through, which means more electrons can go through, so it's actually a lower resistance. So it's kind of a tricky thing to think about. Okay, now here's one. So below we will have a circuit with a resistor and a wire, which will have the larger current. And so there's a really big, thick resistor. If you want, you can imagine that these are the same kind of materials. And so a really thick resistor and then a really skinny wire. Which one will have the larger current? And assume that this this circuit has been hooked up for a while, so it's sort of had time to think about things. All right, discuss this with your neighbors and see what you think. Okay, so let's call time. I think that's everybody. Let's give ourselves maybe a few seconds. Again, if you haven't entered an answer, please enter in your answer now. And this is great. I agree with the majority, but there's definitely some confusion here. Anybody want to tell us what they were thinking on this one? And, if you want to tell us what you were thinking for the wrong answer, that can be helpful too, because it can help us sort of think about where everyone's at on this. Anybody? Yeah. So there's only one path to take? Okay. So we'll find that if there's, as a general rule, if there's only sort of one path to take, the current will end up being the same in that path. And so that's a good rule to remember. Anybody else have some thoughts about this one? Yeah.
When a circuit is in a series, then the current will just be the same throughout the entire water. If you kind of sponge up a pipe at a certain point, the water flow is still going to be the same throughout the entire.
Okay, great. Good way to think about it. So again, we'll learn in a little bit that when things are in series, which the wire and the resistor are in series, the current will have to be the same. So let's talk about this a little bit more. So those are both great ways to think about it. But now, some people, I don't know, maybe we're thinking, well, we just sort of talked about how the current in this resistor should be slower than the current, or whatever. The current in the resistor should be different than the current in the wire. So what's happening? And actually, in real life, what happens is our wires, we're going to make our wires really, 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 really small resistances. Okay? Now, how do we do that if they're really skinny? Well, we make them incredibly high resistivity. Okay? And in fact, when we do problems, we're going to almost always ignore the resistance of the wire. We're going to assume that it's so small that you can ignore it. Okay? And so what will happen initially, okay, is that the electrons will sort of cruise through the wire really fast and then start going through this thing really slow. Okay? And so initially, the current in the wire will be higher than the current in the resistor. And so for most of our problems, we're going to be talking about what we call steady state. And that's, if you give the circuit a couple seconds to kind of figure out what's going on, it reaches steady state. And that'll be the situation we'll be looking at in general. And so what happens is with these wires, the electrons cruise really fast through here, and then they slow down. And so what will tend to happen is the electrons will start to kind of form a line. Okay, so one will come through maybe, and then there'll be one that's sort of stuck here, okay, and then another that's kind of stuck, and so you get this backup of electrons, and then pretty soon this electron here no longer wants to get over here so bad because there's a whole bunch of electrons. And so this lineup tends to slow down the flow of the charges through this wire to the point where the current in all parts of this circuit will end up being the same. Okay, and so our general rule that I think some people were saying is that the current, once it reaches steady state, will be the same in all parts of a closed loop like this. This is a nice closed loop. That means there's no other wires going anywhere else or anything like that. And if not, the electrons will bunch up at a certain point and resist the flow of electrons. And this thing is called feedback. And so this happens in circuits, and so that sort of will occur. And so sometimes our intuition about this stuff can be a little bit tricky. And so the system naturally makes the current constant in all parts of this circuit. Questions on that, anybody? Okay. And so let's see, since electrons are evenly dispersed throughout the wire, why would some parts be more positive than other parts? Yes, I'm not sure what they're asking on that one there. So I'm not sure where we're getting, so we'll move on from that one. Sorry about that. Okay, so quickly, I just wanted to mention something. So my branch of physics is condensed matter physics. I don't know, has anyone ever heard of that? It's sort of like almost nobody ever has. Okay. So it's the branch of physics concerned with the study of very large numbers of strongly interacting particles. And so there's a lot of things from the everyday, like solids and liquids. There's some more exotic things. But basically, like the way I think about it is a person in condensed matter physics, sort of like the first ones, the questions they were asking were, why do some things conduct electricity and other things don't? Right? And another question that a condensed matter person would have asked a long time ago is, why are some things magnetic and some things aren't? All right? And so if you take, in this field, years ago it was called solid state physics. It's sort of changed since then. But it's important to realize that, so what you're dealing with solids is an incredibly large number of atoms, right? And so, in this class, like in the last couple of slides, we had problems where there was like 2 electrons or something, and we could find the exact speed of the electron at some point. There's a certain point where you can no longer do that. Like right now, I think computers can actually follow the path of something like 13 particles or something like this. Okay, some small number exactly. Okay, so sort of if you know the exact force between the particles and the exact speeds, you can actually figure out what's going to happen after that. And if you get larger than that, you can't actually know exactly what's happening. And so the stuff that we talk about when you have large numbers of things, and the example here would be this model we have of the conduction of electrons, it's a model. And so it's not necessarily real. We're not sort of taking everything into account. It works really well, okay, in some situations, but it's a model. So I just wanted to kind of warn you that this isn't always true. And there's some cases like superconductivity. Okay, you may have heard of this. So there's some materials that if you get them really, really cold, all right, their resistance goes to 0. Okay, it literally goes to 0, which is kind of a crazy idea, right? And you can't explain that with our model. Okay, so these electrons in these solids are sort of acting as quantum mechanical objects, and so it gets pretty complicated. And so here's some, so superconductors have unusual magnetic properties. So here's a small permanent magnet that levitates above a disk of high-temperature superconductors. So you get some pretty interesting things with superconductors. And you'll hear people talk about high-temperature superconductors. So basically, when they first found these things, it was like super, super cold temperatures that this would happen. Like you need to get like liquid nitrogen to sort of see these effects. But they're getting to the point where they're getting sort of ones that happen at higher temperatures. And the goal would be to get like a room temperature superconductor, because having 0 resistance would have a lot of applications But the big thing I want to get at is these models we're looking at. You can kind of think that, oh, these must be perfect models, but they're not. Okay, they're models, they work in a lot of cases, but there's some cases where they don't work. And so I just wanted to kind of warn you about that a little bit. All right, and so here's one thing, like I was getting at, the whole Ben Franklin issue, which is that the actual charges that move are electrons, but because they're negative, it makes the math kind of difficult. And so we're going to sort of switch back and forth when we talk about circuits. Okay, if I'm talking about sort of the microscopic, like what's happening, I'll talk about the electrons. But when we talk about sort of trying to solve for the current in different kinds of circuits, it's easier to imagine that it's the positives moving. Okay? And if you think about it, if I have positives moving this way and negatives moving in the opposite way, the effect is the same thing. Okay? Because it's like negatives going backwards is the same as positives going the other way. And so the effect has, there is no difference really in that. And so it just makes life much easier to talk about the current moving as a positive charge. And so that's what everyone does in physics when we're solving circuits. And so it's confusing, but it's easier than sort of always having these negative signs when you're thinking about electrons. So why wasn't the direction of current flow ever changed to the same direction as electron flow? And that's basically why. I've actually seen some books do that. Like, I don't know, who's electrical engineers in here? Do you guys still use like a positive current when you're talking about things, or what do you guys do? I don't know. Yeah, I think most people do that. But I've actually seen some places where they actually use the electron flow. So it's a little confusing, but it just makes our math easier, I think. All right, so here's our big law that we're going to start working with now, Ohm's law. So V equals IR. So higher resistance, lower current. And so here is kind of a nice way to write it. And so this says that the current is kind of like this battle between the voltage and the resistance. Okay, so the higher the voltage, the higher the current will be, and the higher the resistance, the lower the current will be. And you sort of have this fight between the two. Resistance, we didn't say this yet, but the resistance unit is ohms, and we use this letter here to reflect that. And so this is the equation we're going to use as we talk about circuits and try to understand them better. This is sort of our general rule. And again, this is another thing that's a model. Okay, so our conductors, most conductors work like this. Okay, they work under Ohm's law, but there are some materials that don't work like Ohm's law. And so it's not a general thing, so you just got to be careful about that. And resistor, again, it's a device that resists current. It is the same thing as a conductor, and we use this sort of teethy looking thing here as our model for our resistor. And so what we can do then is start talking about, and then this is just a real quick thing. So generally in a circuit, the resistance of the connecting wires are very small, and we can neglect them, okay? And so they're super, super small, and so we're just not even going to worry about them. Now, occasionally you'll have a book problem where they'll be like, okay, assume that you have to think about the wires or whatever, okay? But in general, if there's resistors there, we're going to assume that those resistors have a really large resistance, much larger than the wire. And so the way this will work is again, in general, our current is equal to the change in voltage, right, over the resistance. So that's sort of the idea. And basically, we're going to assume that the resistance is so tiny, and so actually, probably a better way to write it is like this here. So we're going to assume that with wires, the resistance is so small that it's zero. And so when you have the current times R, the change in potential will be zero. And so we're going to find that as we go through a circuit, all the elements in the circuit will give us a little change in potential. And we're going to assume that with the wires, that the R is just so small that that change in potential is zero. Now, in real life, it's there. It's something like, 0.000001 or something. But it's the kind of thing you can neglect and not really affect your final answer so much. Okay? And so that's one thing we're going to do with resistors. And we'll call those ideal wires. Now, our goal for the first couple of lectures here is to go through and basically take our circuit and break it down into the simplest circuit in the world. Okay, and so here's the simplest circuit in the world. It's a battery of 24 volts and a resistance of 8 ohms. We use Ohm's law, and we divide 24 by 8, and we get that the current is 3 amps. Okay, and so this is, our goal is to basically break down our circuits to something like this here, kind of like we did with capacitors last time. Okay, but in general, we're going to have more complicated circuits that we'll need to spend some time breaking down. And so let's start by looking at some situations where there's more than one item. And so here, we love working with light bulbs. Light bulbs are just resistors, right? And so a light bulb is connected to a battery in case A. In case B, an identical light bulb is added in series. What happens to the brightness of the original bulb? And we'll talk more about this as we go on, but there's two things. The brightness of your bulb, okay, goes like the current is one of the things that it goes like. Okay, so if you have identical light bulbs, the current is one way to think about how bright they are. So think about this and see what you come up with. Okay, I think we're getting most everybody answered here. And so let's talk about this one. And I agree with the majority, but there definitely is some confusion here. And so let's talk about this. So I'm going to say it decreases. So someone tell me, what were you thinking with that one? Yeah.
There's more resistance over the entire loop, so the current should be that would lessen the brightness.
Okay, that's a great way to think about it. So there's more resistance in this circuit. Now, how do we know there's more resistance in this circuit? That's what can be tricky sometimes. Anybody have another way they thought about it? That's a good way to think about it, I think. Anybody else? Like, how do we know that these two light bulbs, so these two light bulbs are in series, how do we know that there's more resistance, right? So our rule for series is if I go through one of them, I have to go through the other. There's no other choice. So these are in series, and the way that it works, like probably the easiest way to think about it, is I have our relationship for resistance. So resistance is rho L divided by A. And what you're doing here is if you think about each resistor as having some length, I don't know, maybe it's like this here. What happens is now I have two resistors of length L. And so the length of my resistor is now 2L. So it's increased. And so if the resistance is bigger, if we go back to our equation I equals VR, right? So if my resistance goes up, my current must go down. And so my current going down, and then the current through your light bulb, if it's identical light bulb, will give you an indication of whether it's brighter or not. Questions on that? So we did pretty good on that one, I think. Okay. And so that gives us to this idea of series wiring. So when your two resistors are in series like this, okay, then you can think about the equivalent resistance. So we're going to do the same kind of stuff that we did with capacitors. The equivalent resistance is just going to be the sum of them. All right, and if you think about it, it's just, again, you can think about it sort of like this here. The equivalent resistance is, so if you assume that if these are the same material and the same cross-sectional area, then you're just adding those two links. So it's like the two Plinko boards together, instead of just 1. And so the equivalent would be those added up. Okay? And so if you were good at working on the capacitor problems we had from last time, then you'll be good. You can use a lot of those same skills here too, but just be careful because the rules we have are opposite. So it's a little bit tricky. The rules for actually doing the calculations are opposite. And so the equivalent resistance of resistors in series is just the addition of the resistors. Would be what I would say there. And so kind of, tying in together everything we just were talking about. Questions on that, anybody? Okay, so let's do something then, an actual math question. So in the circuit below, what is the voltage across R1? So let's think about this. Okay, so now just in the interest of time, so hopefully you've had a chance to think about this. Let's talk about this one. So I agree, the majority did come out with this one here. And so let's go through and do this. Now, what we'll try to do is do setups like this. And so just like with the capacitors, my goal is to replace those 2 resistors with 1 resistor. So here's my 12-volt battery. And in this case, we just learned that to replace 2 in series, you add them together. And so here it would be 2 plus 4, and I would get resistance here of 6 ohms. All right? And so then we go to our Ohm's law, because what do we have? We have the simplest circuit in the world, right? And so it's just 1 resistor, 1 battery, and so we just say 12 volts divided by 6 ohms, and I get 2 amps. Okay? So now that could have been the question we were asking, but here we wanted to know what is the voltage across that battery. And so what happens is another thing we know that we've been talking about is that the current, okay, that comes through 2 things in series is the same. And so basically this battery is sending out 2 amps of current, and it goes through both of these 2 guys here. And so we can figure out the change in voltage across R1 is going to be the current times R1. So that'll be 2 amps times 4 ohms. And so that's 8 volts. I think that's the question we asked. And then the other thing you can do is the change in voltage across R2 is I times R2. And so in this case, it would be 2 amps times 2 ohms and 4 volts. And a thing that we'll talk about more next time is that the 8 and the 4 add up to 12. And so for series, okay, the voltage drops across these 2 guys will add up to the same as the battery. Okay, I'll be down here if you guys have any questions. Thank you.